Hi, this is Mrs. Schultz, and I'll be recording this video on how to make slope fields and also connecting slope fields to Euler's method for approximation. Let's go. So let's go over how to create a slope field. Notice that in Euler's method, we're essentially just finding the slope at each point and then tracing the curve through. So like we get this y value and then we find its slope and then we're tracing that to a new y value, all right? And then we find its slope and this tells us how much to go up and over, and we find another new y value. And then this tells us how much to go up and over, and we find another new y value. We'll go over more than that later, but this interpretation suggests a way of finding graphical solutions for differential equations, as we'll see now. Don't worry about making it perfect. All right, suppose dy dx equals x plus y minus 1. Draw a small line segment at each point on the graph below. The slope for each line segment should roughly match the value of dy dx. So let's get started. So I need to come up with a table of x, y, and then dy dx equals x plus y minus 1. All right, and I'm going to have many points. I'm going to put all of these points if I need to on here. So let's start, for instance, let's start right here at 1, 1. Okay, so at 1, 1, what would the slope be? So it'd be 1 plus 1 minus 1 was 1. Lots of ones. So what I do is I make a shortish line with a slope of 1. All right, let's see about this one. Let's see about 1, 2. So what would the slope be here? 1 plus 2 is 3, minus 1 is 2. And then, so that means I make this. Now you might say I can't do exactly a slope of 2, as long as your slope of 2 looks steeper than your slope of 1. All right, let's do, this point. So 2, 1. So 2 plus 1 is 3, minus 1 is 2. The ones cancel out, you just get 2. So this slope matches that one. So whatever you decided for the steepness for that one, try to make it match. If I go over, let's do 3, 1, the slope is going to be 3. So I'm going to make this even steeper. All right, yeah, that looks steeper to me. So hopefully you get the idea. So can you please pause the video and finish making this slope field? And then when we come back together, we can see the answer. All right, and we're back. So if you could check your work, and this is what you should have gotten. Now, let's keep moving. So in physics, you might have seen magnetic field lines, which are similar to differential equations. If you're familiar with Maxwell's equations, they describe this. And if you're more interested, that's something to Google, like relationship between Maxwell's equations and differential equation slope fields, or YouTube it. So let's do part B. So the graph above is called a slope field. Use this slope field to trace a solution to the differential equation going through the point 2, 0. So let's find 2, 0. It's right here. So I'm gonna trace a solution through this. And so right here, that just means I'm following this through. And so I notice that as I go to the right, my slopes get steeper. So I'm not going to go all the way to this point. I'm going to make it get steeper as I go. So maybe something like, and then right when I get here, I should have this steepness. So maybe something like this. I don't want to make it look too vertical. And then here, I notice that it's flattening out. Like this is 0, this is 0. So it's going to flatten out like there. So I'm going to make it flatten out. And then this is hard for me to maneuver. Let's see. And then, so this will look like that. All right. So, and this is something you could be asked to do on the AP test, or on my test is to trace a solution to this differential equation. And so this is a lot like Euler's method in that I find a y value. So I find a y value. So like say, I find the y value 0 for the x value 1, and then I trace the slope of 1 some bit away. Let's say I go a quarter of a way, and now I'm here. And then I have a slope of a higher slope. So maybe the slope here is like 1.25. That would correspond to this column instead of 1. And then I go and I make it a little steeper, and I trace that over another quarter. So I'm here, and I find my new y. That would be like if I'm here. So I just wanted to relate those two. All right, so we did that. Trace another solution to the diff EQ is a shortcut to saying differential equation, this time going through the point 0, -1. All right, so as I trace this through, if I'm starting here, as I go to the right, it looks like I'm getting, well, this is the same slope, but as I go down here, I'm getting a little less, a little steeper. So I think it's angled like that. And then here, I'm going to end up heading toward this. So if I follow this through, if I were to, so as you go to the right, as I go to the right, oh wow, I should have made these better. As I go to the right, looks like it's approaching this slope. So I'm going to approach that slope and that line. So it's going to look like this. All right, so we did that. The more you practice these, the more it'll be easier to see, and approximating is fine. Okay, so now trace, how is the line y equals -x important in terms of the solutions to this differential equation? So this, hopefully you feel the asymptotic nature of it. So it's a slant asymptote for the solution, for the solutions. And so even if I were to, let me move this down a little bit. Even if I were to start somewhere else, like here, I would still head toward this asymptote. My middle would be different, but I would head toward there for my end behavior. Yeah, so that's the solution to that. I want to go over, so now let's go on to the next page where we do a little bit of practice, and I want to talk about that. So this is a multiple choice, so I want to talk about how to notice patterns in multiple choice. So match the following slope fields below to one of the diff EQs. Let's see here. So right here with multiple choice like this, instead of just taking a rote approach, I want to think about what the solutions would look like overall. So I'm going to match each of these is matched with one of each of these. And so how do I tell which one? I could plug in different points, like the point 1, 1 to each one and see, does this have a slope that matches 1, 1? Does this have a slope that matches 1, 1, etc. But I want to look for overall trends. And so these are, they're right above in your book. So these are good tips of looking for trends. Look for the places where the slopes are 0, for instance. So here, the slope, this equals 0 when y equals 0. So you want to look down here and you want to say when y is 0, that's along the x-axis, are the slopes here all 0? Well, no, they're not. So 1 does not match with this. Are the slopes here all 0? Yes. Here, yes. This, no. So when y is in the numerator, so if I call these A, B, C, and D, when y is in the numerator, then I'm going to have slopes of 0 along the x-axis. So this 1 and 3 could match with B and C. So these are B or C. And then these, when x is in the numerator, the slope is 0. And so that's along the y-axis, you have 0 slope. So A and D. So this is like A or D. All right, look at the slopes along the x-axis, y-axis. So we just did that. Look to see if the slopes depend only on x or only on y. Or see if the slopes are positive or negative. And we could have also done vertical too. So we know this is undefined and there's vertical when x equals 0. So for B and C, we'll notice that these are both vertical. All right, but let's sub in like 1, 1. So if I substitute in 1, 1, so at 1, 1, dy dx equals 1. So let's see if that's B or C. So is here the slope 1? Looks like it. Is here the slope 1? No, it's -1. So this matches with that. So 1 is B, 3 is C. and I will let you do the other two on your own. So pause the video and do it, and then we'll come back together. All right, and we're back. So this is A, and this one is D. All right, I will see you next time. Bye.